All right. Unfortunately, neurotransmitter transporters are classified not by the type or chemistry of the transmitter, but rather by the counter ion and co-transport ions that are part of its getting across gradient. So these are mostly secondary gradients that are utilized in order to move the primary substance. And typically, the ions which are co-transported are sodium, counter-transported potassium, co-transported would be hydrogen or hydroxyl. And those transporters that utilize sodium, potassium, and hydrogen are called the sodium solute symporter family, or SSS. Different class or family of transporters utilize sodium and chloride both as co-transported, and these are the neurotransmitter sodium symporter family, or NSS. There are some transporters which only take advantage of the hydrogen ion gradient, that is, they go from more acidic to less acidic environments, and these are called the amino acid, polyamine, and organocation, cation being used in the abbreviation APC family. So these are actually named after the substrate. And then there's some orphan transporters, mostly coupled to hydrogen ion movement, also part of this APC family. It turns out all of these families are part of a much greater gene family called the solute carrier gene family, SLC, for solute carrier. And this family has hundreds of isoforms and different proteins in it. It's huge. So we're principally looking here at the SL1, SLC1, SLC6, etc. subclasses in that family. So what are the major transporters and which neurotransmitters do they transport? In the sodium solute symporter family, we get the glutamate transporters, which are excitatory amino acid transporters, and there's 5 of them. They have numbers 1 through 5. And that's what principally takes care of glutamate. For GABA transporters, GAT1, the transporter, but it's a member of the neurotransmitter sodium symporter family, as are the glycine transporter, the serotonin transporter, the dopamine transporter, and the various versions of the norepi or noradrenaline transporter, and also a choline transporter and some other amino acid transporters. Those transporters that take advantage of the hydrogen ion gradient turn out to be all of the vesicular transporters. Vesicular glutamate transporter, vesicular monoamine transporter, which is utilized for epinephrine, norepinephrine, and serotonin, vesicular acetylcholine transporter, vesicular inhibitory amino acid transporter for GABA and glycine. So the vesicular transporters hang together, but none of these are segregated by the neurotransmitter biochemistry. They're rather classified according to the co-transport ions, and you just have to learn the names. I have posted on the Moodle website, again, some crib sheets that I've made up summarizing lots of the details of the different kinds of transporters at the plasma membrane and at the vesicular membrane, and some of their major characteristics in terms of what are the counter ions, and some interesting information about things that they might bind or be involved in biologically. So how do these co-transports look? For the SSS family, we have 3 sodiums moving from extracellular to intracellular down the sodium concentration gradient. Hydrogen moves in the same direction, which would be a symport, as well as the neurotransmitter moving with the sodium. The countertransport here is for potassium. So depending upon the charge on the neurotransmitter, this movement would probably have a net charge associated with it, since there are 4 inward positive charge movements and 1 outward positive charge movement. So that would be net 3 inward plus the charge on a single transmitter. So there would be clearly a current associated with that transporter itself. For the sodium chloride family, the sodium symport family, we've got both sodium and chloride, 2 sodium and 1 chloride, and 1 neurotransmitter, which would have at least a positive charge for the sodium moving in that may or may not be neutralized by the type of neurotransmitter. So how do the transporters work at a molecular level? To the best of our knowledge, it is quite complex and multi-step. Considering the excitatory amino acid transporters that transport glutamate, we envision this kind of a model being how that transporter operates. In the presence of sodium binding, the first sodium opens some kind of a gate that allows glutamate to come into from a vestibule on the outside to the inside of the transporter molecule, where another sodium ion also binds. That closes the gate, and this vestibule then closes and fills up as well, as conformationally the bound internalized molecules and ion begin to move towards the other side, where a new vestibule forms on the inside of the membrane, and again then a gate can open to expel both one of the bound sodiums and the trapped glutamate, and then the second sodium would be released, and the cycle can begin all over again. So the conformational changes here are very, very important.
Transporters appear to have, besides the normal sodium binding in the interior of the molecule, they have currents associated with the movement of transporter across